Hello everybody. Today I will discuss the topics about the quantum harmonic oscillator. I will introduce the equation of motion approach to derive the ladder operator A and a dagger. So let's begin. First of all, the Hamiltonian of the quantum harmonic oscillator is this. Usually, your professor often will introduce the ladder operator A equals to this 2m omega over h bar x plus I square root m omega h bar p, and a dagger is this. However, for beginners, this is quite tricky and hard to think about this. But today I will introduce the equation of motion to derive such kind of the operators. First of all, let's review the Heisenberg picture. And it has the equation of the motion dA dt equals to 1 over IH bar, H bar, the communication, the commutation of the A and the Hamiltonian. So let's recall the basic commutation relation. Equals IH bar. And it's the equation of motion we can write is let's calculate the commutation relation. Plus p x p bracket equals to IH bar. Similarly, we can derive the omega square x square equals be caution here there's a sign minus since x. Omega square x. So we can derive the second order differential equations, that is d by dt p over m is this, and minus omega square x. So we can easily solve this second order differential equations by use some mathematical you can solve this, and by solving this we can get x equals to a plus b exponential I omega t. Here A and B are the coefficients that needs to be determined. So first of all, we consider the relation x is a Hamiltonian operator. So x equals x dagger, which means a dagger e minus I omega plus I omega t plus b dagger exponential minus I omega t. So we can compare the coefficient. We have the relation a dagger equals to b and b dagger equals to a, operator a. So we can get what we have get is a equals exponential minus I omega t plus a dagger a exponential I omega t. So, and similarly, we can get p equals to m dx dt. We get m dx dt. So, get the similar relation. M minus I omega t exponential I minus omega t plus a dagger m I omega t exponential I omega t. So let's rewrite this. So we can get x equals to a e I minus omega t plus a dagger e I omega t p over I m omega equals to minus a e minus exponential I omega t plus a dagger e I omega t. We can solve this. We can solve a and a dagger. A is minus p I m omega in I omega t. A dagger equals to 1 over 2 x plus p minus I m omega e I minus omega t. And here we can get the commutation relations by a and a dagger equals to 1 over 4 x minus p over I m omega x plus p over I m omega. And we simplify this, we can get p over I m omega plus minus p over I m omega x. So is h minus 2m omega. So we'll bring this into the Hamiltonian, so we want to represent the Hamiltonians by a and a dagger. So let's do it. H Hamiltonian is 1 over 2m x squared plus p squared plus 1 over 2m omega square x square. We take p is im omega square minus a e t square plus 1 over 2 m square x is we simplify this formula, we can get m omega square a dagger plus a dagger a. Here we apply the commutation relation. This part is a dagger plus a dagger a. So we can get m omega square plus, what is the commutation relation here? H bar. So we have the plus omega. If we want to normalize the commutation relation, we can use a delta equals to a over root of the h bar over 2m omega, and a delta dagger equals to a dagger over omega 2m omega. So can find this is our familiarized commutation relations. So Hamiltonian can be written as the h bar a dagger a plus 1 over 2. So here we get the fundamental relations, and we can find a delta is x plus I p. Okay, have a rest. This is the first part. We derive the fundamental relations and we diagonalize the Hamiltonian. In the next part, I will introduce how to solve the eigenvalue problems, and by this kind of the ladder operator. Alright, before we start, let's do some little corrections. Here, the inverse relations here, there should be a ei omega t e minus I omega t. We limit t goes to 0, so this equals to 1, and we can get a relation. This is a very good good questions. Then let's solve the eigenvalue problems. First of all, we assume the En is an eigenstate with the eigenvalue En. Here is our assertions. Act on the operator A act on En is also the eigenstate of the Hamiltonian. So shall be the A dagger act on the En state En. They are all eigenstate of Hamiltonian. So before we do this, let's calculate some commutation relations. H commute with A is H bar omega dagger A this is 0, so can get this is 1. So we get H bar 8 and minus, this is minus 1. A dagger H bar can get H bar A dagger. So let's calculate HAEN equals to the commute of AH plus AH X on EN minus H bar omega A So here we can find the En is the eigenstate with respect to the eigenvalue En minus H bar. So we denote this as the En minus 1. And similarly, we can calculate a dagger En equals to so here we to is this one is so a dagger En is the eigenstate of the H and with respect to the eigenvalue En plus H bar omega. So a dagger En C n plus 1 prime n plus 1. Then we need to fix these two coefficients so the problems can be solved. Here we want to discuss something about the ground state. ground state should be determined by the operator E0 equals to 0, which in coordinates representation we can write as the partial x phi x. Here to save time, this leave as an exercise to solve these partial differential equations. This is a little bit tricky. As we have discussed above, we can find AEN operator AX down the EN is Cn minus 1 EM with index n minus 1. A dagger C prime n plus 1 EM plus 1. So we have the first relations En. The modulus of the AEN is equals to minus 1. This can also be written as the dagger AN. So these two so we can find C prime A equals to Cn minus 1. Also, we get another relation by the commutation relations. A and A dagger commute X on the En. Dagger minus. So we can get take this relation Cn square minus Cn minus 1 square equals to 1. So since AE0 is to C we can calculate C0 equals to 1, C1 equals to 1 plus 1, the Cn equals to n plus 1. So we can get n minus, and by the relation C prime n equals to Cn minus 1, So we combine A dagger A, E N X, and finally we find the eigenvalue problems can be solved. H E N A dagger A plus 1 over 2 and plus 1/2 E n. So here we have solved the eigenvalue problems. The eigenstate En can be calculated by the derive. First of all, we can find the ground state, and then we can use the A dagger operator to calculate the higher energy state, and its eigenvalues are h bar n plus 1/2. So today's lectures are over. This is the brief introductions on the quantum harmonic oscillator. I hope all of you can find it interesting and understand it.